So now let's start talking about the quality of our unstructured meshes. So let's look at an unstructured mesh first for our test case. So this is a quad mesh. So let's just go into Gmesh and make this into a triangle mesh. So we'll also derive this from scratch, but right now let's let's look at the mesh and the quality, and then we'll build the mesh again from scratch. So let's just use a triangular mesh, because that is the one we are going to use for our coding. So this is a nice triangular mesh, and this is of order 2. So let me just take order 1. So yes, so this is our triangular mesh, and as you can see, this is more refined towards the circle, towards the inner circle, and it is more sparse towards the outer end, right? So naturally there is some stretching or some bending which is happening inside each element, and so we need to make sure that the element quality is good. If we look at a mesh which is having slightly more complicated features like this, so now you can simply see that there is some stretching happening here, right? So between these two, so whenever you have a complex geometry, you can see that the mesh will struggle to model this geometry. So we need to make sure that the mesh is correct, and this obviously also depends on the problem as well as on some very straightforward metrics which are same for any kind of problem. So one of the most straightforward metrics is the Jacobian, which we just talked about, the Jacobian of transformation, or you could think of it as the area, which is scaling your actual physical to your master element. So so basically you can think of, so let's go to the whiteboard, and so you could think of four kind of basic parameters, you could say. So one is that your Jacobian should be greater than 0. So since Jacobian is just scaling your area, so you could think of it like, I mean, naturally it is just going to be greater than 0, but sometimes what happens is that we already talked about the Gmesh ordering. So Gmesh is going to count the nodes of each element in a certain way. So if Gmesh is counting counterclockwise and you count them clockwise, so in that case, due to that error in the coding, the Jacobian can appear negative, and then you are just using negative terms where you should be using positive terms, so your code will just go wrong. And so that's one point. The second is also that if you look at this element, so if this is your triangular element, okay, so what would happen if your element was like this? So this would start approaching almost a straight line kind of situation if you start making it thinner and thinner, right? So there are multiple ways of following this. One is that you can check the aspect ratio. You can also check for the angle, right? So the problem here is that once this starts becoming more and more like a straight line, so your Jacobian will really become smaller and smaller. And remember that we are taking the inverse of the Jacobian to compute our derivatives, right? So you take an inverse of something that is really close to 0, so this will just blow up. And then even if you have just one element like this, this will just blow up and create some unphysical effects here, and you might even get some unphysical values, some blow-ups here, and then those blow-ups will diffuse. So just one bad element is enough to ruin your entire simulation. So since we are looking at isotropic case here, like a diffusion kind of problem here, so we really want a well-rounded shapes which are like more or less symmetric. So so you could think of that the minimum angle we can say that it should be greater than 20 to 30 degrees, right? So we could take that as one of the parameters. We could also say that the aspect ratio should be greater than 2 for it should be less than 2, right? Aspect ratio should be less than 2. Anything greater than 2 is not acceptable. Or you could use even higher values here, maybe even 3 or 4 is okay, but let's try to keep the mesh as constrained as possible, and the Jacobian obviously has to be positive. You could also define gradation in your mesh. So if the gradation is really rapid, so if this change is the change in the mesh from the inner boundary to the outer boundary, if this is really rapid, then also you might have some issues. So really you need a very smooth change here, and Gmesh takes care of all of these problems really well, and especially in this kind of a very symmetric case, it handles it very well. And when it cannot, it will just show an error here, that it is not able to manage that kind of a good mesh. So for this gradation, you could just define an area fraction. So for example, you could take the area of the element upon the average area of each triangle. Okay, and you could just look for orders of magnitude change. If you are seeing the change in terms of like thousands or 10,000s, of course it depends on your geometry as well, and it depends on your problem, your geometry, all of these things, but you cannot really have orders of magnitude change between both of these parameters. So if the order of magnitude change is like 3 or 4, I mean, that's really a problem. So these are the 4 basic kind of points which you can look at, and in case of this problem, which is simple diffusion, it really doesn't matter whether you have a skew in one direction or not. But in case of different physics, you could purposefully probably increase the aspect ratio in one direction. Okay, and it might allow you to capture the physics. You also have shell elements, for example. So it really depends on the problem. In case of the next course, which we are going to launch for Navier-Stokes, so there we will have convection along with diffusion, and then meshing becomes really important. Also, if you have a turbulent boundary layer or any boundary layer which you are really trying to capture, where this is your wall and you have this boundary layer here, so really you are having a very sharp gradient which is coming out, right? And for capturing this, sometimes we use wall functions, and for wall functions, then your meshing has to be really correct. So for example, if you are using a Robin wall, so these are just your Robin conditions, and for turbulent flow, for example, you use log law, for example, to so if this is your wall and you are having this as your turbulent flow profile, so you can use a wall function, which is a very simple approach, and typically you just place your first Gauss point at a node which is present on the log profile, and you use a Robin condition, just like we calculated the the effect at infinity. We just put a shear stress, tangential shear stress condition, and we just have to capture the correct tangential shear stress at the wall. And for this you require really correct meshing, and so in that case meshing will have even added importance. So really this depends on the problem, and for our test case, which is really simple, a diffusion problem, we really need to deal with only these 4 parameters. All right, so let's go to a code where I'll just show this, and so this is just your same problem which we are solving, your diffusion problem, and we'll solve this in MATLAB. But so this is just the solution, and here you can see I have put 4 parameters here, these 4 parameters to define the quality, and this is the quality check which I am showing here. Okay, so there are 904 elements total, and so this is the minimum of the determinant of Jacobian, which is, of course, we just have to maintain it as positive. We have kept the angle as 40, so you are getting 8 elements which are greater than 40. So 40 is pretty large, actually. Even 20 or 30 is okay. If I just increase this, so this would just be an just a perfectly triangle with equal sides. So this is basically impossible, so in an unstructured case, so almost impossible, right? So you will you just get 904 which are not following this quality check, and there are total 904 elements. So you can just use this kind of check for every mesh. So here I have just put the aspect ratio. So if I just take the aspect ratio as 1, then this will not pass, right? But I have kept an aspect ratio of 2, and this is because it's a very simple mesh, so there is really no chance of Gmesh going wrong here. Right, so you can see that the aspect ratio is 0, so you are not finding any elements with aspect ratio of 3 and beyond 3. So and this is your area fraction. So if I just try to make this 0.2, for example, so you can capture some 72 elements. So so really this is very easy, and you can just run this kind of a quality check every time for your mesh, and this is a good practice. For our diffusion case, we are pretty much we can use the Gmesh itself, and it will help us generate good meshes. So Gmesh also has these higher order tools, right? And in higher order tools you can even put a target Jacobian range, and when you really have skewed meshes, so you can do this regularization, and you can arrange these meshes. So when we basically when we deal with this problem, maybe we can have this problem right here. So let us try to apply regularization on this mesh. But first we'll just solve a simple test case which just is a monopole. So let's just do that. Let's start off by developing our mesh in Gmesh, and then we can just change our solver as well to the 2D solver. So let's just do that.